Hi, we're continuing in the kinetics unit, and this video is about rate laws. This is a really important video, and so make sure that you're taking really good notes and that you understand what's happening. We're going to practice rate laws by looking at different free response questions from AP exams. All right, so first of all, what in the world is a rate law? Well, it's just going to be an expression, and it's going to show how the rate depends on the concentration of the reactants. So we're going to be looking at like, well, what if we double the concentration of this reactant? What does it do to the rate? Does it go twice as fast? Does it quadruple the rate? How does it affect the rate? Or does it affect the rate at all? And so we're going to be looking only at the reactants and how the concentration of the reactants affect the rate. A rate law looks something like this. It says the word rate, or you would have the rate that's been measured is equal to K. This is a lowercase k. It's not the capital equilibrium K. And then all the concentrations of the reactants. So in this case, we only had one reactant, the nitrogen dioxide. So the molar concentration of NO2 raised to some exponent N. Now that N is called the reaction order, and we're going to talk about it in a minute. First of all, let's look at little k. Little k is called the rate constant, and it does change with temperature. And so the effects of temperature on a rate is due to the value of K changing with temperature. Remember the equilibrium K? Remember it did change with temperature as well. Well, this K will change with temperature. All right. N is reaction orders, and for us, we're going to be looking at 0, 1, and 2. So 0 order, first order, and second order reactions for the most part. They can be a fraction, they can even be negative numbers, but we're just starting out, so we'll keep it fairly simple. Now, that N, that reaction order can only be determined experimentally. So you're not going to get any of the information from the balanced equation. All right, so these reaction orders in the rate law can only be determined experimentally. And calculating a K, you'd have to have a rate and a concentration in the reaction order in order to solve for a K. All right, so let's look at some important points. First of all, the concentration of the products do not appear in the rate law. It's just the reactants. And those reaction orders, and we're going to use exponents like M and N, you cannot look at a balanced equation and tell what they are. They have to be determined experimentally. So sometimes you might see this type of rate law called a differential rate law, but we're just going to call it a rate law. And one more time, this shows how the reaction rate depends on the concentration of the reactants in a reaction. This is called the method of initial rates. And so what we're going to do, we're going to look at the initial rate of a reaction, so the rate just after the reaction starts. And you're always going to have several experiments that are carried out. And so you may have like 3 or 4 experiments where you change the concentration of a reactant and see what effect it has on the rate. And this is how we determine the reaction orders. So this is what data looks like. So in this reaction, we have the ammonium ion and the nitrite ion reacting to give us nitrogen and water. So our rate law would be rate is equal to, so maybe I should write this down for you. The rate law would look something like this. Rate is equal to K times the concentration of our reactant, ammonium, times the nitrite ion. And then this is raised to some order, and this is raised to some order. This is what a rate law looks like. And you've got initial concentrations of your ammonium ion and of your nitrite ion, and then you've got these rates that were measured somehow. All right, now the first thing we want to do is if we wanted to solve for K, we easily could do that. You take any of these experiments, and what you do is you put in the rate. You would put in the concentration of NO2 and raise it to the N power, and the ammonium and raise it to the M power. But we have to figure out what those reaction orders are before we can solve for K. All right, so let's go ahead and do that. Now we're going to compare two experiments, and we're going to keep the concentration of one of the reactants the same, and then we're going to change the concentration of the other reactant and see what effect that has on the rate. So let's look at experiments 1 and 2. We don't do anything to the ammonium concentration. It's the same, but look, we doubled the concentration of the nitrite ion. And what happened to the rate? Well, it also doubled. When you double the concentration and the rate doubles, that's called first order. So this reaction is first order with respect to the nitrite ion. So this right there is a 1, and you need to write it. Okay, I've done this work to figure it out. So if whatever you do to your concentration, you keep everything else the same, let's say that we had changed this concentration, we made it 10 times larger. The rate would have mimicked what you did to your concentration. It would have gone up 10 times. All right, so whatever you do to your concentration, if you double it, the rate doubles. If we tripled it, the rate would have tripled. That's called a first order reactant. All right, let's look at the ammonium ion. Let's try and figure out what the M is. We need an experiment where ammonium's concentration changes, but the nitrite does not. So now we're looking at experiments 2 and 3. All right, so ammonium concentrations double, but the nitrite stays the same. And again, the rate doubled. And so it is also first order in the ammonium ion. And so we need to write a 1 here. So our M is a 1 and the N is 1. And the language sounds something like this. This reaction is first order with respect to ammonium, and it's first order with respect to nitrite. All right, so let's write that rate law. So here we go. The rate is equal to K times the concentration of ammonium raised to the first power times the concentration of nitrite raised to the first power. Now, we determine the order of the reactants by using the data. It's the only way to do it. All right, now, the overall reaction order is just the sum of M and N. So the overall reaction order for this reaction is 2. So this reaction is a second order reaction. Okay, now, sometimes, well, always, they're going to ask you to justify your answer. How do you know it's first order? And you can use words. You could say, well, when I kept the ammonium concentration ion the same and I doubled the concentration of the nitrite, the rate doubled, therefore it is first order with respect to nitrite. Or sometimes it's not quite this easy. You may need to figure it out, and this is a way of justifying it using some math. So let me show you another way to do this. You can pick 2 experiments, and I think I want to pick experiment 2 and experiment 1. So if you look back at that data, experiment 2's rate was 2.7 times 10 to the negative 7th, and the other rate was from experiment 1, it was 1.35 times 10 to the negative 7th. Okay, so this is experiment 2. So experiment 2's rate law would be K times NH4 to something times NO2 to something. And this would be divided by K. And that should have an N. This would be NH4. And now let's plug these values in from that data. So let's see, this is a 2 is equal to K. From this experiment, it was 0.1 molar. And this was 0.1 molar as well. Divided by K. I got the 2 here by dividing these rates. And this stayed the same. It was 0.1 molar. And this went in half to 0.005. molar. Okay. All right. I think this is 0.01 maybe. I think so. Whatever it is, these cancel, and this and the k's cancel. So 2 is equal to, and whatever this was, it was 2 raised to the n. So therefore, n must be 1. It's first order. All right, so this is just a way to justify your reaction order. There's lots of these justification practices in your book, and we can practice it also in class. So that's a way to justify your answer or to figure out your reaction order if you just can't tell from looking at the data. All right, calculating K. All right, once your reaction orders are known, you pick one experiment, you plug in all the values, and you calculate the K. So let's go ahead and why don't you guys do it for experiments 1, 2, and 3. And what you do is you plug this in as your rate is equal to K, this raised to the first power, and then this raised to the first power, and solve for K. And then try it for the second experiment and the third experiment and bring those answers to class. Now, what you should find is that the value of K should be the same in all the 3 experiments. It doesn't matter what experiment you pick. Remember, K only changes if your temperature changes. So go ahead and do the calculation for K. Now, the value of K has units, and they're different depending on the overall order. And so a lot of times they might just ask you for the units of K. So remember it was a rate was equal to K, and then it was a molarity to the first and a molarity to the first, okay? So this unit is molars, and I think it was per second, but always check that unit on time. Make sure it's like seconds if you're writing seconds. Sometimes it's minutes, sometimes it's hours, but I think this one was seconds. All right, it's equal to K, and then a molar times a molar. All right, so this unit, when it's an overall second order reaction, the unit for K is going to be molars per second divided by molars squared. So what in the world is that going to be? Well, that's going to, when you do all the simplification, it's molar to the -1, seconds to the -1. All right, so that is how you calculate K. So you're doing that for homework, and then making sure you have the right unit. In class, we're going to have you calculating what the units for K would be for third order and 0 order and so forth. Okay, so just to kind of summarize, if you have a first order reactant, you first of all keep the concentration of all the other reactants constant except the one you're interested in. And if the rate is mimicking what you're doing to the concentration, then it's first order with respect to that reactant. And that's what we saw. Second order, again, you keep all the concentrations of your reactants constant except the one you're interested in. But if you change the concentration of the one you're interested in, the effect on the rate would be like squared. So in other words, if you doubled a concentration, the rate would be quadrupled. Or if you made your concentration 10 times greater, the rate would go 100 times faster. That's called 0 order. Whatever you do to your concentration, if you double it, you square that 2, and the reaction would go 4 times faster. Okay, and then there's 0 order, and this is really interesting, and we'll talk about why something is a 0 order reactant when we get to mechanisms. But a 0 order means that you change the concentration of the reactant and it has no effect on the rate whatsoever. Okay, and that's called a 0 order. All right, well, we're going to stop with that, and we're going to practice this a lot.